Swayam Prabha. Digital India. Educated India.
So, I think the answer is much more straightforward, at least to begin with. The answer is, okay, so I know that at time t, length of the velocity vector, right, which is this, is giving me the speed at which that particle is moving on my curve. So can I compute the distance till time t? Right, we know distance is speed into time,
Yes,
as
sir.
far as the speed is constant. Otherwise, we integrate, isn't it? I hope this is not very strange. What is in the integrand is nothing but the speed at some time t, right? Multiply by an infinitesimal time interval and just add all of this together. So that's basically your integral. So if I start at some time alpha, right, and at different times between alpha and t, I travel at different speeds, right? So in order to find that at time t how much distance I have traveled, I'll have to integrate, right? So this is speed, this is time. Okay,
Sir, alpha is what? Sir, can you please
alpha
repeat?
is, let's say, the starting time. So you can see in this notation motion of the particle between two time instants alpha and beta. So my starting time is, let's say, alpha.
Sir, I have a doubt that won't it give a distance on a straight line? Means, don't we shouldn't we take a r d theta and that integrate?
R d theta. Where is this R coming from?
Means for finding arc length.
But what is R?
Radius of curvature of that curve.
Why should it be R d theta?
Sir, I think
Means
taking the consideration of circle, we say that arc length is RD theta.
Right,
no,
right.
no, I am not considering it as a circle, but a curve may change its radius of curvature. So we are just using the expression that
But
defines
what
the
would
radius of
theta
curvature.
be?
D theta means we will write theta d theta in the form of time. Means d theta we will do d theta by dt, and then dt will be going to right hand side, and then we will express it into the terms of dt,
So, for
and then
example,
we will integrate.
like in this case, how will you find 0, 0, let's say 1, 1? This is my curve. Then, so how will you compute the distance traveled?
This is for this, it is straightforward. It is a straight line, so we can directly go by distance formula.
No, no, but so it doesn't make sense if your formula works only for one case and not for the other, right? I mean, you can also, okay, let's say
But
this
sir,
one.
if we see for an unusual curve,
Mhm.
and according to that integration, we apply that integration to the finding the distance of the linear motion. It's
but
not in a planar motion.
not in a planar motion in the sense.
We use integration if the curve is velocity versus time.
Yeah, but that's what it is, right? So at every point P, I know what is the velocity. Velocity is x dash t, y dash t, right? So that's your velocity. So just using this same concept that distance is speed into time, right? So speed at every time it changes. So what can I do? I can sort of make an assumption that at a particular time the speed remains a constant in a very infinitesimal time interval, right? So if I then just add up the distance traveled in each infinitesimal interval, I'm going to get the total distance traveled. And okay, as far as the discussion where I want to take this, it doesn't really matter what is here. Okay, but so let's say there is a function that gives you at every time t how much has the particle traveled, right? Can we agree on that? Whatever you, I mean, you may want to use radius of curvature, but to me it seems a very complicated way of doing
No,
something that is
no, sir. It's okay. I made a mistake. Sorry, sir.
no, that's okay. No need to be sorry. I mean, it's expected. That's fine. But if you're not convinced by this right hand side argument, just think there would be some equation that will give you the distance traveled by the particle for every time t, right?
Yes, sir. We
Yes,
can
sir.
find a function or assume a function like that.
Right. So the question is, instead of using the time parameter, right? Gamma is a function of time, isn't it? As of now, instead of using or describing the position with respect to time, can't we describe it with respect to the distance that it has traveled?
Yes, sir. We can.
We can, right? So let us, and we are still describing the same path, okay? So if the distance traveled is s units, then the point is at the same position as the point has reached after traveling for t units. Got it? I mean, do you understand this equation?
Yes, sir.
So with this, so this is a new description of the same curve, right? Because I'm saying that the curve has not changed. The position are the same. It's just that instead of describing it with respect to time, it is now described with respect to the distance it has traveled. So if I make this change, what is the speed of the particle which is described using the distance parameter? So what I'm doing is I'm just changing the units of time, right? The s is a function of t, right? So basically t gamma 1 by dt, sorry, t gamma by ds into ds by dt, right? I'm just using the chain rule. I'm assuming you all are familiar with that, right? Are
Yes,
you
sir.
familiar? Right. So then this is, what is ds by dt? Rate of change
Speed.
of distance with respect to time.
Speed.
Speed.
Speed. What is on
Speed.
the right hand side? That's also speed, isn't it? d gamma by dt.
Yes, sir.
So length of this, length of the speed of the new description, what would that be? These two have the same length, isn't it?
1.
So this would be 1. And that's exactly what we want. Okay? We want that you should describe the curve using a moving particle such that the speed of the moving particle is always 1. Okay, and the simplest way to do it is to describe the particle with respect to the distance it has traveled. Sorry for the interruption. I'm working from home, so right. Okay, so to get back to this discussion, try to imagine this. You describe the motion of the particle with respect to the distance that the particle has traveled. Once you do that, the speed has to be 1. All right.
Yes, sir.
So once you realize that, then right, so gamma 1 s is the description of the same curve with respect to s. Okay, so now if I want to find the curvature of the curve described by gamma, that would be the same as the curvature of the curve described by gamma 1, isn't it? Because they are still describing the same curve, the same path. But the difference is gamma 1 is a unit speed description. So I can compute the curvature by just computing the length of the double derivative of gamma 1, which is what we described. This notation, I am not sure if you are familiar with this notation. Are you?
Yes, sir.
2 vertical lines, you familiar with that?
No, sir.
No,
Okay.
that is not, I think.
No. So let's say V is a vector with 2 coordinates, okay? Vx comma Vy. Then the length of the vector would be, what would be its length?
Under root Vx square plus Vy square.
Right. So this equation is what is denoted in short by this expression. Okay, so I'm just using just a new notation to denote length of the vector, which is put inside these pairs of vertical lines. Okay, and so once you are okay with the notation, I think this equation should not be unfamiliar, right? It's just the length of the acceleration vector. Okay, so you can now compute, you can sort of take and compute its length. The derivation is so large derivation, but it's just mechanically substituting this for that and so on and so forth. So I'm not going to discuss the derivation, but then you get something like this at the end. Okay, so the acceleration vector, remember the right hand side is with respect to the original description, which may not be a unit speed description. Okay, so using this new description, we can compute the curvature of a curve which is described using a non-unit speed curve. Okay, in this way, and you can see that it looks very close to equation somebody gave for radius of curvature. Right here, the assumption was that the curve can be written as, right? So you can see that this is roughly inversely proportional to the radius of curvature equation given by someone. It's just the vector cross product of acceleration and the velocity. You'll get a vector, take its length, divided by the length of the velocity vector to the power 3. Okay, now this in principle you can do it. It's not very interesting though. So let's move on. Now let's look at this particular curve, right? And I'm assuming that gamma is a unit speed description. Let's look at these 2 points, P and Q on the curve. So is the curvature the same for P and Q?
It can be same or it can be different.
So, okay.
The graph is symmetric.
Yes, the graph is the same. That's what I wanted to tell. That whatever is this, I have just sort of inverted to get this curve. So although I have not been able to do a good job in drawing this, but you can assume that the curve is similar at P and Q.
Sign might be different, but
Sign might be
magnitude
different.
is same.
So, okay, so if you look at our definition of curvature, right, either this or this doesn't really matter. What do you think would be the sign of the curvature?
Positive only.
Only positive, right? In the right hand side expressions, it's clear that it's length of vectors. Lengths cannot be negative. So curvature is always, the way we have computed it, it's always a non-negative number. Okay, but then you notice this points P and Q, right? Although the amount of curvature is the same, but these 2 points are different, right? And if I draw the tangent vectors at these points on points near this, so by the way, I did not explicitly mention it, but the velocity vector would be nothing but the tangent to the curve, right?
Yes, sir.
Yes, sir.
Okay. If you look at how the velocity vector is changing around these 2 points P and Q, around P, the
It is
rotating in a,
decreasing.
whereas around Q, the tangent vectors are rotating in an anti-clockwise direction, right? The rate at which these 2 tangents rotate around P and Q may be the same, but the direction in which they rotate are the opposite, right?
Yes, sir.
So can we sort of capture this as well in our definition of curvature? Okay, that's our next aim. And that is what is called signed curvature. So let's see how we can capture this. So let gamma s be a unit speed curve. Okay, so which basically means speed at any parameter value s is always 1. So if gamma s can be described by 2 functions, x of s, y of s, x describing the x coordinate, y describing the y coordinate, right? Speed being 1, it basically means this equation, right? dx by ds squared plus dy by ds squared is always 1 for all values of s. Okay, so this is nothing new. So both sides you have functions of s. Okay, so we should be able to differentiate both sides with respect to s. So what happens when you differentiate the left hand side? Twice dx by ds times d square x by ds square. Similarly, twice dy by ds to d square y by ds squared. Right hand side, since it's a constant function of s, it doesn't change, right? So the differentiation of the right hand side will of course be 0. Is this understood? Yes or no?
Yes, sir. It is understood.
Understood. Okay. So rewriting this, right, and ignoring the 2, you can divide both sides by 2 and write it as this vector times this vector is equal to 0. And remember, what is this vector? It's just your acceleration vector, right? And this is nothing but your velocity vector, right? So what does this equation mean? I'm sure you have, but just for it would be good to get a confirmation. You have seen the scalar product or the dot product in your physics or math courses earlier?
Yes, sir.
Yes,
Yes.
sir.
So then I hope you recognize that this tells us that your acceleration vector and your velocity vector will be perpendicular to each other. Right? The dot product being 0 means the two vectors have to be perpendicular. Yes? So then let us look at another vector which is perpendicular to the velocity vector. Okay? And here I am again using the fact that your velocity vector is nothing but is the tangent vector to the curve. Is that fine? That understood? Your velocity vector is nothing but, remember, since the description is unit speed, it will be a unit vector. So this velocity vector would be nothing but the unit tangent vector to the curve. Okay? And then what we have derived is that the acceleration vector is perpendicular to your velocity vector. Apart from the acceleration vector, there is another geometric vector which is also perpendicular to the unit tangent vector, and that is something we call the unit normal. Okay, so we define the unit normal as the vector obtained by rotating the velocity vector or the tangent vector anti-clockwise by an angle 90 degrees or an angle pi by 2. Okay, so for the same curve at this point, if this is my tangent, rotate it by an angle pi by 2 in an anti-clockwise direction. So that will be your unit normal at this point. Similarly, at this point, if this is your tangent vector, rotate it in an anti-clockwise direction by an angle pi by 2, you get your unit normal vector. Okay? So now we have two vectors which are perpendicular to your velocity vector or your tangent vector. What should be the relation between these two vectors? Should I repeat the question? Question is, you have your acceleration vector which is perpendicular to your velocity vector or the unit tangent vector. You have your unit normal which is also perpendicular to your velocity vector. So what is the relation between the acceleration vector and the unit normal vector?
Perpendicular to each other.
Acceleration dot n cap also 0.
How can that be? So we are talking of planar curves, right?
Okay, then it will be parallel.
Yes, sir. Then parallel or anti-parallel?
Then parallel or anti-parallel, right? So
Cross
N and
cross product 0.
A, cross product 0, right? So more than that, right? So A, the acceleration vector will either be parallel or in the opposite direction of n cap. Okay? N cap, by its notation and its definition, we know it's a unit vector. Okay? How about acceleration vector? Is it a unit vector?
Wait, didn't get you.
The question is, the acceleration vector and the unit normal are aligned, right? Either in the same direction or in exactly the opposite direction. The next question is the acceleration vector a unit vector? So is A either equal to n cap or equal to minus n cap? Is that true?
Sir, it might not be true in all cases.
So what will it not, and in what cases will it not be true? Or what is the length of that acceleration? That is something we just defined, right?
So can we rather say A cap might be equal to N cap or minus N cap?
Exactly, right. There's no doubt about it. But the question is, how about the vector A? What is the length of that vector called? That's here, right? It's sitting here. The curvature, isn't it?
Yes, sir.
So then, in either cases, I can say that the acceleration vector is equal to some scalar times the unit normal. And because we are now allowing this possibility that A can be in the opposite direction of n cap, this scalar or this number that we are now calling kappa s. Okay, it can be both positive as well as negative. And the magnitude of the acceleration vector is something we had already defined as the curvature. So whatever is the magnitude of this, it has to come from curvature. The only difference is now, apart from that magnitude, there is also a sign to it. So taken together, this number kappa s at a particular point is what is called the signed curvature. Okay? So you can see over here my velocity vector, or all of this will turn in this direction, and so the acceleration vector you can expect will be in this direction. Whereas here my velocity vectors are turning in this direction, and so your acceleration vector would also be in this direction. Okay, so in this case, the acceleration and n cap, so the curvature will be positive, whereas in this case, since acceleration is in the opposite direction of n cap, my curvature would be negative. Okay, and this of course depends on how you define your n cap. So this is just a convention that you define the unit normal as a vector obtained by rotating tangent in the anti-clockwise direction by an angle pi by 2. You can replace anti-clockwise by clockwise as well. In that case, the signs would reverse. Okay, but in no case would the signs of the curvature at both these points remain the same, which is aimed for, right? We wanted to distinguish this point on the curve with this point on the curve. Okay, there's another way to capture the sign curvature. Now we said that gamma s is a unit speed curve. Okay, I know I am almost out of time. I will finish the class in 5 minutes. Okay, so please give me 5 minutes time only. Now gamma dot s, right, is a unit vector, okay, in the plane. So this is 1. So then if this is my gamma dot s as shown in the picture, I can say it is cos of some angle and sine of some angle, right? And see, the length of this vector cos phi s and sine phi s will also be 1. Okay, so it sort of matches. You can show that at every point this will be the case, right? Because at every point this vector gamma dot s is a unit vector, so it can be written as cos of some angle and sine of some angle. Now, this angle will of course change depend from point to point. At this point the angle would be something like this. At this point the angle would be this. At this point the angle is this. Okay, so you have a function phi that gives you at every parameter value s between, let's say, alpha to beta, the angle called the turning angle. And again, you can relate this intuitively to, let's say you are driving a vehicle on this path. Right? By what angle would you have to turn your steering in order to remain on the curve? That is basically the intuition behind turning angle. Okay. So basically implies that at every point on the curve, the velocity vector, since I'm using a unit speed curve, can be written as cos phi s and sin phi s. Right? And now, straightforward observation that if I differentiate, we get the velocity vector on the, the acceleration vector on the left. On the right hand side, I should get my signed curvature times the normal vector. So that's what I'm going to do. The t square gamma by ds square minus sin phi s d phi by ds and cos phi s d phi by ds. d phi by ds is a common scalar. You can bring that out. Times the vector minus sin phi s cos phi s. You can see that length of this vector is 1. And if I take the dot product of this vector with this vector, see that it's 0. So this is nothing but your unit normal. Okay, so your acceleration vector is d phi by ds times n cap. And so the rate of change of your turning angle is nothing but your signed curvature. Okay, so again, the amount by which you have to turn your steering wheel at every moment can be interpreted as the curvature. Again, intuitively, I hope it makes sense. More curved the road, the faster you will have to turn the angle, because remember, you are not allowed to change your speed. Okay, so going at the same speed, more curved the road is, more you will have to keep on turning your steering wheel. So the rate of change or your motion of your steering wheel is directly your sine curvature. If you have to turn your steering wheel in one direction, the curvature will have a particular sign. If you have to turn the steering wheel on the other side, the sign will change. Finally, I wanted to prove this theorem. I don't think we have the time. I'll just give the statement and then we'll maybe take it up tomorrow. Okay, and it's a very important theorem if you are looking at application. So let us just read the statement carefully. Okay, So given two unit speed curves, gamma 1 and gamma 2, let us say they have the same signed curvature function. Call it kappa s. The question that this theorem tries to address is, if I give you two curves which have the same signed curvature function, can the curves be different? Okay, is the statement clear? The theorem tries to address this question. I give you two curves which have the same signed curvature function. Then it's trying to address this thing, that how different can these two curves be? What this theorem suggests is that the only difference in the two curves is that they can be either located at different parts on your xy plane, or they can be oriented in a different way. So you may find that the two curves are rotated by different angles. It's a very powerful theorem. Application point of view, let's say you want to recognize objects from images, or you want to sort of do a classification, or you want to match the two objects, right? Shape or the curvature is going to be same if the objects are the same. Okay, so you can use the curvature information as a feature. Okay, but again, let me not get into applications. This statement is what we will prove, and it relies only on calculus that you have studied so far.